Hello. Today I am Professor Rose with a lecture on differential equations and integration. What is a differential equation? A differential equation is an equation between specified derivatives on an unknown function, its values, and known quantities and functions. Many physical laws are most simply and naturally formulated as differential equations, or DEs. For this reason, DEs have been studied by the greatest mathematicians and mathematical physicists since the time of Newton. Ordinary differential equations are DEs whose unknowns are functions of a single variable. They arise most commonly in the study of dynamical systems and electrical networks. They are much easier to treat than partial differential equations, whose unknown functions depend on two or more independent variables. Ordinary differential equations are classified according to their order. The order of a differential equation, as to find the largest positive integer n, for which an nth derivative occurs in the equation. Thus, an equation of the form theta of x, y, y prime equals 0 is said to be of the first order. A differential equation is a mathematical equation that relates some function of one or more variables with its derivatives. Differential equations arise whenever a deterministic relation involving some continuously varying quantities modeled by functions and their rates of change in space and or time, expressed as derivatives, is known or postulated. Because such relations are extremely common, differential equations play a prominent role in many disciplines, including engineering, physics, economics, and biology. Differential equations are mathematically studied from several different perspectives, mostly concerned with their solutions, the set of functions that satisfy the equation. Only the simplest differential equations admit solutions given by explicit formulas. However, some properties of solutions of a given differential equation may be determined without finding their exact form. If a self-contained formula for the solution is not available, the solution may be numerically approximated using computers. The theory of dynamical systems puts emphasis on qualitative analysis of systems described by differential equations, while many numerical methods have been developed to determine solutions with a given degree of accuracy. Many fundamental laws of physics and chemistry can be formulated as differential equations. In biology and economics, differential equations are used to model the behavior of complex systems. The mathematical theory of differential equations first developed together with the sciences where the equations had originated and where the results found application. However, diverse problems, sometimes originating in quite distinct scientific fields, may give rise to identical differential equations. Whenever this happens, mathematical theory behind the equations can be viewed as a unifying principle behind diverse phenomena. As an example, consider propagation of light and sound in the atmosphere and of waves on the surface of a pond. All of them may be described by the same second-order partial differential equation, the wave equation, which allows us to think of light and sound as forms of waves, much like familiar waves in water. Conduction of heat, the theory of which was developed by Joseph Fourier, is governed by another second-order partial differential equation, the heat equation. It turns out that many diffusion processes, while seemingly different, are described by the same equation. The Black-Scholes equation in finance is, for instance, related to the heat equation. Examples. A simple example of a differential equation is dy dx equals lambda y, where lambda is a constant. The unknown is y, and the independent variable is x. The equation involves both the unknown y as well as the unknown dy dx, and for this reason is called a differential equation. We know from calculus that y of x equals ce to the lambda x, and c is a constant, satisfies this equation since dy dx equals d dx ce to the lambda x equals c lambda e to the lambda x equals lambda y of x. The constant c is uniquely specified once we give the initial condition, which in this case would be to give the value of y of x at a particular point x naught. For example, if we impose the initial condition y of 0 equals 3, then the constant c is now determined, i.e. c equals 3. Consider the differential equation dy dx equals y squared, subject to the initial condition y of 0 equals 1. This dE was solved in calculus using the method of separation of variables. First, write the differential equation in differential form. dy equals y squared dx. Now, separate all variables, all x's on one side and all y's on the other side. dy over y squared equals dx. Now, integrate both sides. Negative 1 over y equals x plus c, where c is a constant to be determined. Solve for y equals y of x. Y of x equals negative 1 over x plus c. Now, require y of 0 equals negative 1 over c to equal the given initial condition, negative 1 over c equals 1. Solving this gives c equals negative 1 hence the solution we want is y of x equals negative 1 over x minus 1. An example of a second order ordinary differential equation is f of x equals m d squared x over dt squared, where f equals f of x is a given function of x and m is a positive constant. Now the unknown is x and the independent variable is t. The problem is to find functions x equals x of t such that when substituted into the above equation, it becomes an identity. Here is an example. Choose f of x equals negative kx, where k is greater than 0 is a positive number. This equation then reads as negative kx equals m d squared x dt squared. Write this ordinary differential equation as d squared x dt squared plus k over m x equals 0. You can check that x of t equals sine of the quantity square root of k over m times t. Can you find other functions that satisfy the same equation? One of the problems in differential equations is to find all solutions x of t to the given differential equation. We shall soon prove that all solutions to this example are of the form x of t equals c1 sine of the square root of k over m times t plus c2 cosine of the quantity square root k over m times t, where c1 and c2 are arbitrary constants. Using differential calculus, one can verify that this can be substituted into the above equation to satisfy the differential equation. Recall the differentiation formula: d dt sine of omega t equals omega cosine of omega t, and d dt cosine of omega t equals negative omega sine omega t, where omega is a constant in the above constant, omega equals square root of k over m. It is another matter to show that all solutions to these equations are of this form. Newton's principle of determinacy. The initial state of a mechanical system, the totality of positions and velocities of its points at some moment in time, uniquely determines all of its motion. It is hard to doubt this fact, since we learn it very early. One can imagine, in a world in which to determine the future of a system, one must also know the acceleration at the initial moment. But experience shows us that our world is not like this. Many interesting ordinary differential equations arise from applications. One reason for understanding these applications in a mathematical class is that you can combine your physical intuition with your mathematical intuition in the same problem. Usually, the result is an improvement of both. One such application is the motion of pendulum, i.e., a ball of mass m suspended from an ideal rigid rod that is fixed at one end. The problem is to describe the motion of the mass point in a constant gravitational field. Since this is a mathematics lecture, we will not normally be interested in deriving the ordinary differential equation from physical principles. Rather, we will simply write down various differential equations and claim that they are interesting. However, to give you the flavor of such derivatives, which you will see repeatedly in science and engineering, we will derive from Newton's equations the differential equation that describes the time evolution of the angle of deflection of the pendulum. Let L equal length of the rod measured, say, in meters, M equal the mass of the ball measured, say, in kilograms, G equals acceleration due to gravity equals 9.8070 meters per second squared. The motion of the pendulum is confined to a plane, this is an assumption on how the rod is attached to a pivot point, which we take to be the XY plane. We treat the ball as a mass point and observe there are two forces acting on this ball. The force due to gravity, mg, which acts vertically downward, and the tension vector t in the rod acting in the direction indicated. Newton's equations for the motion of a point vector x in a plane are vector equations. Vector f equals m vector a, where vector f is the sum of the forces acting on the point, and vector a is the acceleration of the point, i.e. vector a equals d squared vector x dt squared. Since acceleration is a second derivative with respect to time t of the position vector, vector x, Newton's equation is a second order ordinary differential equation for the position vector x. In x and y coordinates, Newton's equations become two equations. Fx equals m d squared x dt squared. Fy equals m d squared y dt squared, where fx and fy are the x and y components, respectively, of the force vector f. We see, upon resolving vector t into its x and y components, that fx equals negative t sine theta and fy equals t cosine theta minus mg. T is the magnitude of the vector t. Substituting these expressions for the forces into Newton's equations, we obtain the differential equations. Negative t sine theta equals m d squared x dt squared. T cosine theta minus mg equals m d squared y dt squared. From this, we see that x equals L sine theta and y equals L minus L cosine theta. the origin of the xy plane is chosen so that at x equals y equals 0, the pendulum is at the bottom. Differentiating with respect to t and then again gives x dot equals L cosine theta theta dot, x double dot equals L cosine theta double dot minus L sine theta theta dot squared. Y dot equals L sine theta theta dot, y double dot equals L sine theta theta double dot plus L cosine theta theta dot squared. Substitute these into our above equation to obtain negative t sine theta equals ml cosine theta theta double dot minus ml sine theta theta dot squared. Cosine t theta minus mg equals ml sine theta theta double dot plus ml cosine theta theta dot squared. Now multiply this by cosine theta and the second by sine theta, and add the two resulting equations to obtain negative mg sine theta equals ml theta double dot, or theta double dot plus g over L sine theta equals 0. This ordinary differential equation is called a second order equation because the highest derivative appearing in the equation is a second derivative. The ordinary differential equation is non-linear because of the term sine theta. This is not a linear function of the unknown quantity theta. A solution to this ordinary differential equation is a function of theta equals theta of t, such that when it is substituted into the ordinary differential equation, the ordinary differential equation is satisfied for all t. Observe that the mass m dropped out of the final equation. This says that the motion will be independent of the mass of the ball. If an experiment is performed, we will observe this to be the case. Namely, the motion is independent of mass m. The derivative was constructed so that the tension, vector t, was eliminated from the equations. We could do this because we started with two unknowns, t and theta, and two equations. We manipulated the equations so that in the end we had one equation for the unknown theta equals theta of t. We have not discussed how the pendulum is initially started. This is very important, and such conditions are called the initial conditions. We will return to this ordinary differential equation later. At this point, we note that if we were interested in only small deflections from the origin, this means we would have to start out near the origin. There is an obvious approximation to make. Recall from calculus the Taylor expansion of sine theta. Sine theta equals theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial, and so on. For small theta, this leads to the approximation sine of theta is approximately equal to theta. Using this small deflection approximation leads to the ordinary differential equation theta double dot plus g over L times theta equals 0. We see that this is mathematically simpler than the previous equation. The reason for this is that the equation is a linear ordinary differential equation. It is linear because the unknown quantity theta and its derivatives appear only to the first or 0th power. Linear first-order equations. The simplest differential equation is the one you already know from calculus, namely dy dx equals f of x. To find a solution to this equation means one finds a function y equals y of x such that its derivative dy dx is equal to f of x. The fundamental theorem of calculus tells us that all solutions to this equation are of the form y of x equals y naught plus the integral from x naught to x of f of s ds. Y of x naught equals y naught, and y naught is arbitrary. That is, there is a one-parameter family of solutions. Y equals y of x, y naught. The solution is unique once we specify the initial condition, y of x naught equals y naught. This is the solution to the initial value problem. That is, we have found a function that satisfies both the ordinary differential equation and the initial value condition. Every calculus student knows that differentiation is easier than integration. Observe that solving a differential equation is like integration. You must find a function such that when it and its derivatives are substituted into the equation is identically satisfied. Thus, we sometimes say we integrate a differential equation. In the above case, it is exactly integration as you understand it from calculus. This also suggests that solving a differential equation can be expected to be difficult. For the integral to exist, we must place some restrictions on the function f appearing. Here it is enough to assume f is continuous on the interval a, b. It was implicitly assumed that x was given on some interval, say a, b. A simple generalization is to replace the right-hand side by a function that depends upon both x and y. dy dx equals f of x, y. Some examples are f of xy equals xy squared, f of xy equals y, and the case above. The simplest choice in terms of the y dependence is for f of x, y to depend linearly on y. Thus we are led to study dy dx equals g of x minus p of x times y, where g of x and p of x are functions of x. We leave them unspecified. We have put the minus sign into our equation to conform with the standard notation. The conventional way to write this equation is dy dx plus p of x times y equals g of x. It's possible to give an algorithm to solve this ordinary differential equation for more or less general choices of p of x and g of x. We say more or less since one has to put some restrictions on p and g. That they are continuous will suffice. It should be stressed at the outset that this ability to find an explicit algorithm to solve an ordinary differential equation is the exception. Most ordinary differential equations encountered will not be so easily solved. But before we give the general solution, let's examine the special case p of x equals -1 and g of x equals 0 with initial condition y of 0 equals 1. In this case, the ordinary differential equation becomes dy dx equals y. And the solution we know from calculus, y of x equals e to the x. In calculus, one typically defines e to the x as the limit. E to the x equals, by definition, the limit as n goes to infinity of the quantity 1 plus x over n, all raised to the power of n. Or, less frequently, as the solution y equals y of x to the equation x equals the integral from 1 to y dt t. In calculus courses, one then proves from either of those starting points that the derivative of e to the x equals itself. One could also take the point of view that y of x equals e to the x is defined to be the unique solution, satisfying the initial condition y of 0 equals 1. Taking this last point of view, can you explain why the Taylor expansion of e to the x equals the sum from n equals 0 to infinity of x to the n over n factorial follows almost immediately? Method of integrating factors. If this were of a simpler form, then we could immediately write down a solution in terms of integrals. For it to be of this form means the left-hand side is expressed as the derivative of our unknown quantity. We have some freedom in making this happen. For instance, we can multiply by a function, call it mu of x, and ask whether the resulting equation can be put in the form. Namely, is mu of x dy dx plus mu of x p of x times y equal d dx of the quantity mu x of y. Taking derivatives, we ask, can mu be chosen so that mu of x dy dx plus mu of x p of x times y equals mu of x dy dx plus d mu dx y. This immediately simplifies to mu of x p of x equals d mu dx, or d dx log mu of x equals p of x. Integrating this last equation gives log mu of x equals the integral p of s ds plus c. Taking the exponential of both sides, one can check later that there is no loss in generality if we set c equal to 0, gives mu of x equals exponential function, the integral x p of s ds by integral of x ds, we mean the indefinite integral of x in the variable s. Notice y and its first derivative drop out. And this is a good thing, since we wouldn't want to express in terms of the unknown quantity y. This last equation is precisely the form we are looking for, so we can immediately conclude mu of x y of x equals integral of x mu of s g of s ds plus c. And solving this for y gives our final formula. Y of x equals 1 over mu of x integral of x mu of s g of s ds plus c over mu of x, where mu of x, called the integrating factor, is defined C will be determined from the initial condition y of x naught equals y naught. An example. Suppose we are given the differential equation dy dx plus 1 over x y equals x squared when x is greater than 0, with initial condition y of 1 equals 2. This is of the form with p of x equals 1 over x and g of x equals x squared. We apply the formula. First, calculate the integrating factor mu of x. Mu of x equals the exponential function. Integral p of x dx equals the exponential function integral 1 over x dx equals the exponential function log of x equals x. Now substitute in y of x equals 1 over x integral x times x squared dx plus c over x equals 1 over x times x to the 4 over 4 plus c over x equals x to the 3 over 4 plus c over x. Impose the initial condition y of 1 equals 2. 1 over 4 plus c equals 2. Solve for c. C equals 7 over 4. Solution to the differential equation is x of y equals x cubed over 4 plus 7 over 4x. This concludes our lecture for today. Thank you so much for joining me.